I'm just gonna when I'm doing these streams, I'm just gonna assume that you don't know what I'm talking about, or or you need a refresher. So basically, how arrays work in computers as like a data structure, a way of storing data is think of it like drawers, right? Like each one of these is just one long cabinet, and each one of these squares is a drawer, right? And then you have like a position for each drawer, or it could be a door with a number, however you want to conceptualize it. And then you can store one thing inside that drawer. That's fine, but like there's sometimes when you want to store things in a different structure, right? Because the problem is like, okay, and like if I want to insert a new thing, remove something from the middle drawer here, what I have to then do is, because you can't have these like empty spaces. And so if I want to remove something from this middle drawer here, I then have to take everything to the right of it and scoot it over one, right? Because now there's this empty block here. And so sometimes you don't want to store things in arrays because of that, right? Because everything needs to have an adjacent member. You can't just make holes, because then you're wasting space, right? So, but there's times where like you want to store things in trees, because if you guys aren't familiar with trees, you have like a value and it's a node. So we can actually we're going from heaps to a binary tree. Yeah. So here's a tree. Well, let's do binary search trees, because these are sorted. This is just, now, don't let it fool you, okay? These are all just, this is just a way of representing, like, say you want to have a list of sorted numbers. This is a way of literally doing that. It looks like it may be overkill, but don't worry about it. So this is called a tree, right? This, this might look like a family tree, and that's exactly, it's because it's a tree, right? It's a way, it's called a data structure. It's a way of structuring your data in a way where you can do helpful thing. Like there's trade-offs, right? So if, like I said earlier, if you have an array and you want to remove something from the middle of an array, it takes it takes longer than it would take you to do in a tree. And here's why. So this is called a binary search tree. You have a node in the tree. A node can have a reference to a left node and a reference to a right node. That's it. So those are the very simple rules, right? You have a ball, you have a value, and it can connect to a left value and a right value. And why would you want it to connect? Well, say you want to store numbers in a sorted fashion. So, your first value is 2, and then you want to add a new value, and the value is 1. Okay, well, the rules of a binary search tree are, for every node, if you want to insert a value, the left value needs to be less than the parent node, and the right value needs to be greater than the parent node. And so and what's great about this is then, now this is actually a bad example, because this root node should actually change over time, because if you don't change it right, you start with the number 2. Okay, well then the majority of numbers that aren't negative are greater than 2, right? So this would be a terrible starting point. What you want this to be is really sort of the midpoint, and you can update that as time goes on, but we won't mention that. But basically, you can find and access numbers. Since this is sorted, you can basically cut off an entire the right side of the tree. So say you're looking for 1 in this example. You know that 1 is less than 2. So you just go to the left, and then is the value 1? Okay, yes, it is. Sweet. Okay, we found the value 1. So like finding the needle in the haystack is way more efficient with a binary search tree than it is with an array. Because with arrays, even if they're sorted, it can be, finding the value in the array may take the same amount of time, but replacing it is way less than it is with a tree. So all that to say, like, the way that you store data matters, because you get this, there's the way that you interface and modify the data changes based off of what strategy you use to store your data. So everything is trade-offs. There's nothing that's like the best. You're always making a trade-off and usually the trade-off is either space, so how much memory you're using to store the data, or time. And so like based off of, so if you have, and this is represented in big O is what it's called, big O notation. This is a math thing. Yeah, exactly, Suli. So it's a function, right? It describes how the number of iterations scales with the input size. So, we don't deal really in constants. All we care about is, as the amount of input scales, how does the algorithm, so how does the runtime or space requirement grow as input size grows? So, really like a really bad, time complexity or space complexity would be like exponential, right? Like you can just look at an exponential, growth rate, and then it's like, this is bad because the amount of iterations that's required to say sort your data goes up exponentially with the amount of, data that you have. We don't like that, right? So how you store your data basically gives you these different characteristics, and what sort of algorithms you use give you different characteristics of accessing the data, updating the data, things like that. So like how you store your data matters. And that's basically what all this stuff is about, is like different ways of storing and fetching data so that you can do things efficiently. And these all kind of look like, when you see all these names, like what the hell is a linked list? What's a stack? What's a static versus dynamic array? Sorting, search, all this stuff is fundamental stuff that you use to then build programs where you have things like, a digital Disney fast pass line, or, you need, like say you're storing things in a database. Say you're writing a database, right? You're creating a new database software. You need to understand these things so that you can efficiently store and fetch data. Otherwise, it's slow, right? So anytime that you are storing or fetching data, you are using data structures. And that's why it's very important to understand them, because otherwise, you don't know what you're doing and things can get really slow. Or if you want to build something really complex, you really need to understand, what your options are to see if you can even actually like do what you want effectively. You may need to reach for a different solution because it's mathematically infeasible, or sometimes there is no mathematical way to do it faster. Sometimes you just have exponential complexity. You have to check each permutation of everything. Or, well, yeah, so if you have to check each permutation, that can be a factorial time complexity. And so sometimes, depending on your data set, but it's important to understand that you can measure that, because once you measure it, you can see if you can improve it or not. And sometimes you can't improve it. But, it's knowing your tools, and it's knowing your limits. So just like any other time you need to reach for a tool, you need to know what the limits of the tool are and that you're making a trade-off. You can use a chop saw for everything for safety reasons, but if you want to cut a tree down, you're not using a chop saw, right? You are making a trade-off to use a chainsaw. You can actually cut the tree down, but that comes with increased risk. So you need to be able to respond to that. So the thing is about computers, it's not different from anything. Just like all things are, when it comes down to it, the fundamentals of learning how to do things and learning how things work, I don't like to say that everything is the same, but there is nothing new under the sun. These concepts that we're using to represent data and describe all these computer science fundamentals have existed long before any computer existed or anything like a computer existed on Earth. These are all, everything that we're sort of doing here is a very like sort of fundamental, it goes like much deeper than computer science. It's like information theory. And it's even before we had something called information theory, there are many people on Earth who fundamentally understood these things. And so, and that's the sort of beautiful thing, is like, it's everything, learning, you can learn anything. There's no divine knowledge that somehow is locked away from you. You can really learn anything. And the more you learn, the easier it is to learn other things. And so that's what's sort of beautiful about this, is learning like how things fundamentally work. You can pretty much like
everywhere using a regular binary tree, but with
exactly. And that's what I was saying earlier, is like when you choose these data structures, there are constraints, but those constraints give you these guarantees, right? And that's what's so great about it. And that's why you would store this in an array and not like a binary search tree, because there's a bit of a constraint, which, while it is a constraint, it gives you the opportunity to sort of reason about the structure. You have this structure despite the fact that it's actually being stored contiguously in memory. And not even the fact that it's stored contiguously in memory, which is helpful in some ways, but the fact that you actually do have this literal tree structure, except you can reason about it by accessing an array. And so you always can look things up instantly. I don't think that you can add things instantly. That's probably where this gets really hairy. But you can definitely, and that's why this is in 3 separate sections, but you definitely get a lot of benefits of using an array in this